Hi, my name is Daniel Otamelum, and this is Project 1.5, a counting circuit. The first part of this project is the button input, which uses a 6mm square PBNO button and an active low pull-up resistor configuration. The input is created for each following step in the project. The active low configuration means the inputs to a circuit are high unless the PBNO is pressed and pulls the inputs low. The second part of this project is the NAND gate oscillator, or NGO. This circuit introduces the 4011 NAND chip, which produces a high output unless both inputs are high. The NGO provides a clock signal for the final counting circuit. Clock signals are periodic square waves that oscillate between a low and high state at a constant frequency. There are two resistor-capacitor networks in this circuit. The first one controls how long the oscillations occur for, and the second one controls how frequently the oscillations occur. Increasing the values of the resistors or capacitors in both RC networks will increase the length and frequency of oscillations and vice versa. It should be noted that resistor capacitor network 2 provides feedback to the circuit by discharging into the input of the NAND gate whose output feeds said RC network. The third part of this project is the decade counter that introduces the 4017 decade counter chip. This chip has 10 output counts that go high consecutively as the clock signal advances a count. The divide by 10 output is the output that divides the frequency of the clock signal by 10. This pin is used in future steps in the project to ensure that the counting speed of the NAND gate oscillator is not too fast. Step 4 is the binary up-down counter, which introduces the 4510/4516 chip. Both of these chips work the same way, but the 4510 can only count from 0 to 9 in decimal, while the 4516 can count from 0 to 15. This circuit takes a divide 10 output from the 4017 as its clock input. The circuit displays the advancement in clock signals through 4 LEDs that represent binary digits. There is a reset pin on the chip that resets the count to 0 when high. This is accomplished by wiring an active high PBNO button. Lastly, the up-down pin is wired to an SPDT slide switch, so the direction of counting can be altered. Steps 5 and 6 are the binary counting decimal decoder and 7-segment display. The 4511 BCD chip takes the binary coded number supplied on the A through D inputs and converts it into decimal notation when output. These inputs are taken from the outputs of the 4510 or 4516 counter chip. The 4511 is a 7-segment display driver that converts binary coded decimal numbers into decimal notation on a 7-segment display block. It has 7 outputs, A through G, that correspond to each segment on the block. This counting circuit breadboard prototype uses a common cathode 7-segment display. This means that each LED segment has a common cathode that must be run to ground. Each other pin must be wired high to turn on a segment. Additionally, each segment requires its own resistor to ensure each segment has an equal level of brightness. When using the 4516 counter chip, like I do in this circuit, counts 10 to 15, which are 1010 to 1111 in binary, will display blank. The final step of this project is the encased PCB version of the counting circuit. It works the same way as the breadboard prototype, but the 4510 counter chip is used instead of the 4516, so there are no blank outputs. The PCB is powered by a battery in the 3D printed case through a battery snap that feeds into a terminal block soldered onto the PCB. Again, the circuit can count up and down from 0 to 9 in decimal notation. My name is Daniel Otamelum. Thank you for listening.